Hi, Mr. Corsi here. In question 6 here, we've got a couple of functions with their formulae, and we're asked to find expressions for f of g of x and g of f of x. So let's have a look at how we would go about that. So part 1 asks us to find an expression for f of g of x. Now, straight away we know that g of x is 2x. So let's replace g of x by 2x. Then we have to say to ourselves, well, what does function f do? If something goes into f, for instance a, then this formula tells us we do 3 plus the cosine of a. If theta went in, we'd have 3 plus the cosine of theta. If blob goes in, we'd have 3 plus the cosine of blob. And in this case, blob happens to be 2x. So we'll put 2x in, we get 3 plus the cosine of 2x. So there's our first expression. Let's have a look at the second part. I've swapped the order of these functions round, so this time we've got g of f of x. So the easy part is replacing f of x by the 3 plus cos x. That's what we know f of x is. But now again we've got to ask ourselves what happens when something goes into g. For instance, if we put a into g, formula tells us twice a comes out. If we put theta in, twice theta would come out. If we put blob in, twice blob would come out. And in this case, blob is 3 plus cos x. So we get twice 3 plus cos x. Twice, and that's the whole of 3 plus cos x, which is 6 plus 2 cos x. So there's our second expression. Now let's have a look at part B of this question. Determine the values of x for which f of g of x equals g of f of x. So in this case, we just put down the expressions that we've now worked out. F of g of x we know is 3 plus cos 2x equals g of f of x we now know is 6 plus 2 cos x. And therefore we're sitting looking at a trig equation which we have to solve. The only values we're allowed to use are those between 0 and 2 pi. So we're in radians and we're limited to 0 to 2 pi. Now the first thing to notice is that we've got a cos 2x expression in there, and we know the double angle formula for cos 2x. There's 3 versions of it: 2 cos squared x minus 1, or cos squared x minus sine squared x, or 1 minus 2 sine squared x. So which of these are we going to use? Well, we'll look around at the scenery around about us and see cosine of x. It's all we see in numbers. Which of these 3 versions just has cos x in it? Well, 2 cos squared x minus 1 does. So it would be daft to introduce a sine x into a scene where we don't have the sine x. So let's choose the 2 cos squared x minus 1 version and see what's going on. And you know, it's looking very much like a quadratic equation building up here. If we had something like 3 plus 2c squared minus 1 equals 6 plus 2c, that looks like a quadratic, and would sort it all out with c squared term, c term, and a constant equals 0. So let's shuffle these around to see what goes on. So we have 2 cos squared x. Let's subtract 2 cos x from both sides. And then on the left hand side we've got a 3 minus 1, which is a 2. So let's subtract 6 from both sides, so that 2 minus a 6 will be negative 4 equals 0. And just tidy up the fact that we've got a common factor of 2 in each of the terms on the left. Let's divide both sides by 2 now. So everything on the left gets divided by 2. and everything on the right. Well, that just leaves 0 again. So we certainly have a quadratic expression. It's a quadratic equation we're trying to solve. So let's see if this factorizes in the time-honoured tradition. So our first in each bracket would be cos x. Cos x times cos x gives us cos squared x. Looking at the lasts, 2, there's only one possibility, 2 times 1. And then our outside two terms give us cos x. Our inside two terms multiplied give us 2 cos x. And remember, they have to be combined to get negative 1 cos x. That'll happen if we've got a cos x minus a 2 cos x. So that tells us that the minus goes with the 2 cos x and the plus goes with the 1 cos x. And just check, when you do multiply out, you will get this expression here. And lasts in particular, negative 2 times 1 does give us negative 2. So we're okay there. So we're now sitting looking at one factor times another factor gives us 0. So one or other of these must be 0. So it's a possibility that cos x minus 2 is 0. The other possibility is that cosine of x plus 1 is equal to 0. Now, if that first possibility was true, then cos x would have to be 2. If the second one was true, then cos x would have to be negative 1. So there's a couple of simpler equations that we've been reduced to now. And I think at this stage it's well worth looking at the cosine graph, because after all, the cosine graph tells us in one diagram about the values of the cosine of an angle. Remember, it starts out with a value of 1, goes down to 0, negative 1, back up to 0, and then up to 1 again. And it continues in its cycle in that way. And that's pi upon 2, that's pi, that's 3 pi upon 2, and that's 2 pi. 1 and negative 1. So the values of cosine, we know, alternate from 1 all the way down to negative 1 and so on. So if we're asked to find an angle whose cosine is 2, so way up here, does that graph ever reach a height of 2? No, it doesn't. There is no angle whose cosine is 2. So this part has no solution. So let's look at the second part. The cosine of an angle is negative 1. Now remember, we're restricted to angles between 0 and 2 pi. And yes, there is one angle whose cosine does give us negative 1, and it's pi. So this implies x equals pi. So only one solution. So determine the values of x for which this is equal to this expression is equal to this is x. So x equals pi is the only solution for 0 up to 2 pi. So x equals pi. So that's Mr. Corsi signing out, and thanks for watching this video.